is larger than B. In this case, is this is minus B and minus A and minus B. Okay, so that is our definition of the dot controllers. So for this case, again, let me rewrite this one, AB, and 1 plus S over A, 1 plus S over B. Okay, so now for this case, we're going to draw GC, J omega, will be equal to A over B, and 1 plus J omega over A, 1 plus J omega over B. The same thing here, I'm going to decompose into 3 terms. And in this way, we can superpose the individual plots of these 3 terms, 1, 2, and 3. And by using the information we have, we can quickly put into this one quickly. Okay, so here is the decompositions for phase and magnitude. So that is the first terms. And again, always in dB. And that is the magnitude of the first term and second term. Okay, and that is the magnitude of the third term. Okay, and that will be the composed. So that is the magnitude of GC in dB. Okay, so now again we put everything prepared, and the corner frequencies again will be at A and B. Right now for this scenario, A is greater than B, so A is here, B is here. I can wait for you, then we can begin to see. And once you get this kind of preparation done, then and look at me, let me know you are ready. Good? Okay. So now again, for the first term, that is constant. So similar to what we have done, this is 20 log and A over B, and that is constant all the way through here. So this term is pretty straightforward. For the second term, and the second term is we're going to calculate the magnitude of 1 plus J omega over A here. Okay, so the second term is about this. So we're looking for the information. So that term, basically we have information here, right? So let me copy that information to there. So for that term, we have the asymptotes and intersecting at the corner frequencies, and the asymptotes at the larger frequency have a positive slope. So let me copy that information here. So again, this is corner frequency A. So the asymptotes is like this. So this is 20. Right. Okay. And now for the third term is the magnitude of 1 plus J omega over B. Okay, so that is the inverse of a linear functions. So again, we're looking to here. So that is the one like this. So again, we have an asymptotes, but at the larger frequencies, the asymptotes go to negative slope. So here, this is a corner frequency here, so that is a 1. So this is minus 20. Okay, so again, we can superpose the whole things together. So this one, we superpose the asymptotes first. Okay, then in the second range, in the middle range, this is a zero slope, a straight line with zero slope plus a straight line downward. So that is going to like this. So the slope is negative 20. Okay, and we now go to the higher frequency range. In the higher frequency range, that is a superposition of the three straight lines, zero slope, 20 slope, and negative 20 slope. So basically here will be equivalent to is horizontal straight line with the zero slope here. Be good? Okay, so now again, you can label it. So here is about 3 dB above, and here is about 3 dB below. So you can label it. So that is about here, and that is about here. Okay, and then the superposition of the three curves will label at this value. So this is 20 log B A over B. Okay, so that label at here, and then we can simply kind of the drawing like this. You good? Okay, so for the phase angle, we can also exercise the phase angle quickly. So let me draw that one here. So if you run out the space, you can continue your lecture note after the magnitude, but let me draw the phase angle here. So that is the phase angle of A over B. Log. So that is phase angle of 1 plus J omega over A. And so that is phase angle of 1 plus J omega over B. And these are composed. Okay, so again, for phase angle of the constant term, that is always 0. So we draw this one quickly. Okay. Now we label, for this term, its corner frequencies is at A here. So again, when omega is small, for this case, that is almost 0. So asymptote is something like this. When omega at the corner frequency, that is at 45 degrees. So maybe 45 degrees. And then when omega is become big, approaching to 90 degrees. Okay, so basically that is something like this. Okay. You good? And usually, this kind of the transition range we take is take a range is about 1 decade of this space. 1 decade, that means is a ratio of 10. A ratio of 10 in the log scale basically is a 1 unit. Okay, usually in our exercise of the drawing this transition, we take 1 unit, which means 1 decade of the things. Very good? Okay. So again, for this case, the corner frequency is B. B is here. So again, that is from the 0 degrees and minus 45 and to minus 90 degrees. So basically that is okay, if we take the decades, and so that is something like this. So this is approaching to 90 degrees. Okay, so this is 0 degrees. Okay, so now from here we superpose, so that will be equal to So 0 degrees and 45 degrees and 90 degrees. Let me get everything ready. Okay. So now let me superpose the asymptotes first. And the lower frequency range, basically that is, this is 0 degrees plus 0 degrees, so starting from here. Okay. And then come to the B into the middle range. In the middle range, basically asymptotes is going down like this. Okay, so at B here is about minus 45. Okay, and then keep going to this range. If you superpose, basically you can see that is a 0 and then plus upper trending slope. So basically in this range is something like this one. Okay, and to the very large range, basically that value is minus 90 and plus 90 is back to 0 again. So that is the trend for this. We kind of schematically show them, and for this case I didn't make the complete, but that pretty much can be good as possible. Okay, so now we added up the whole things together, and so for this case we can simply label this 45 and plus something. So basically that is similar something like this. Here I won't criticize how precise the drawing will be, but at least we show the trend for minor drawing. That will be good enough. Be good? Okay. So, any questions? And we spent quite a bit rigorous and going into the details. I think the two will be a very good example here. And compared to the two, this is the lag controllers and this is the lead controllers. From the phase diagram, you can see for the lead controller, its phase, contribution of the phase is always above 0. So that's the reason why we define this as lead controller. For lead controller, by all means, its phase is always above 0. And depends on the selection of the A and B value, the maximum phase could be reaching to 90 degrees. That is the maximum possible value the phase, the lead controller can provide. But depends on the selection of A and B, the maximum value could be less than 90 degrees, say 60. So that means this curve, the feature, the precise quantitative description of this curve really depends on how you modulate your AB value here. If your AB value is very close, then you can kind of be playing a little bit to see what happens. And again, this is the lag controller. For the lag controller, you can see its phase is always negative, but the maximum value of the lag controller won't be greater than 90, minus 90. Minus 90 is the maximum possible phase defect the lag controller can provide. Okay. So again, depends on how you choose the corner frequency A and B, how you choose this kind of range, that can affect the maximum things. So later in the last portions of this module, the frequency design, we're going to talk about how to utilize the two features and to help us to modulate the whole phase features of the controller of certain systems. So right now I would say the two figures, if you like, you can make a mark on this one. I need you to have the two figures memorized in your mind, which means that will be the take home. And later on, we're going to use this one a little bit more details. Okay? Good? Okay, so we're done this section.